Good evening, doctor. This is group SW-ML-23, and you're presenting our project about babesiosis disease detection in animals. Before I start, these are my group members: Arikosos Joel and Garang John. So here is the content of the presentation that we are going to make. First of all, we shall have an introduction, the related work, problem statement, research questions and objectives, research contribution, system architecture, and the description of our data set. Then the results, experimental and simulation, conclusions, and then limitations. Then proceeded with next step, and then acknowledgement. So this is the introduction and the background for our project. Background. Tick-borne diseases are severely affect livestock health and productivity. Babesiosis is one of the major tick-borne diseases that are a big threat to cattle. In tick-borne diseases, we have basically like 5 diseases: the heart water, East Coast fever. But basically, we are going to look at babesiosis in our project. So babesiosis causes anemia, reduced milk production, weight loss, high mortality, and then death. That is frequently confused with malaria plasmodium when viewed under a microscope, because both of them take the ring shape, which may lead to confusion to the person who's trying to detect which disease is that. So our introduction to the project. One of the things that motivated us to do this project is that currently there is a manual diagnosis process that is being carried out in order to determine this disease. For example, doctors currently diagnose the GIMSA stained smears, and this is subjectively. It results to this process is somehow slow. It has chances of the error prone, which may lead to giving over false results to by the doctor. So deep learning enables automated medical analysis, whereby we shall use our model that we've built using machine learning, whereby we shall be uploading our images, the microscopic images, which will be able to determine whether the animal is diagnosed with babesiosis or not. So we shall use CNN in order to detect the parasites in the blood smear images. One of our goals is to ensure that the process is fast, accurate, scalable. It is accurate and scalable veterinary diagnosis. So here are the recent trends or the related work according to our project. Currently, deep learning involves the CNN transforming medical image analysis, making it fast and reliable. Transfer learning enabling high accuracy with limited data, whereby we can have our trained data sets, which you can train our model so that it becomes good, such that if a person just uploads one image, it will be that image that will be uploaded will be worked on faster, and then we get the accurate results. AI-assisted parasite detection from blood smear images, the mobile and cloud-based diagnostic system for road development. Here we shall develop a website or an application whereby the users or the doctors, the veterinary doctors, will use it in order to just upload the image, and then the result to be displayed whether the animal was infected with babesiosis or not. Explainable AI, improving trust and then transparency. Those are some of the recent trends or the related work that we shall consider in our project. So here's the problem statement. Our problem statement is categorized into the domain application problem and then the computation problem. And then our domain application problem, these are the real life challenges that are being solved. For example, the manual blood smear examination is slow, subjective, resulting in delay treatment in rural areas, especially in the northern Uganda. Then there are frequent confusion between babesiosis and similar parasites. For example, the Plasmodium, which causes malaria in animals. The co-infections such as malaria, anaplasma, and other pathogens are common in pastoral systems, worsening the clinical outcomes. So those are some of the domain application problems that we are trying to solve. Then the computational problems, we should develop an accurate multi-class image classifier for babesiosis, uh, comparing it with other lookalikes, for example, like the plasmodium ring, the plasmodium protozoa, which will help us distinguish whether it is babesiosis or malaria. Then the healthy cells, here we have the white blood cells and red blood cells. So if the disease is diagnosed, it will be easier for us to detect whether it is under babesiosis that it is affected, and if it is healthy, it will be under the red blood cell, the red blood cells will be dominating high. So under the competition problem, we have another problem whereby we have severe class imbalances. This happens if we have only, according to, this happens in case we have little data, the little positive data. For example, if since we are looking at babesiosis, if you have little percentage of babesiosis, and then it is versing large data for the healthy, like the red blood cells. For example, if it was a 79, we have a severe class imbalance on that issue. Then need to perform real-time babesiosis detection in the provided microscopic images. Those are the competition problems that we have. On the other side, you have the domain application problems. So then the next slide, we shall talk about the research questions and objectives. Some of the questions that we came up with doing our research is that, can transfer learning on public parasite images detect babesiosis with veterinary grade atlas? That was one of the questions. Then the second question, how well can the model distinguish babesia from morphological similar parasites, for example, Plasmodium? Those are the basic two questions that we came up with, and you're going to find out a solution for them. So our research objective for this case in our project was to prepare and explore a relevant subset of microscopic blood smear images. Under this case, we managed to get some data sets from some websites, which will help us to get these images so that we can train our model to be accurate, perfect, and then efficient. To develop and train a deep learning classifier for babesia detection, and then also to evaluate the model performance using standard metric and confusion analysis, and then to demonstrate a prototype interference tool for the new images. Now, for the last point of demonstrating a prototype interference tool for the new images, here we shall have a well-developed website whereby it will be easier for the users, for that they can just upload their images, and then the processing of the image starts, that we can get results about the uploaded images. Our research contributions and outputs are here. So we developed, these are the things we're going to work on. We developed a focused multi-class babesia detector using efficient net ResNet on the public dataset that we got. Then we built a robust negative set. This will be including the healthy red blood cells, the leukocytes, and then the plasmodium. This will help us to reduce the false positives. We achieved the promising accuracy whereby the percentage was greater than 90 as expected, and this as expected in the babesia against the non-babesia classification. For example, like babesia against the plasmodium classification. Then we designed and deployed a user-friendly diagnostic interface to support practical use in the veterinary clinics. This will provide a clear interface whereby the user will just upload the image, and then the processing takes place. I think I can hand over to the next group mate to proceed with the next slide.
Yes, hello. My name is John Garang, and I'll be taking you through this methodology and system architecture. So, here we hold a simple method and system architecture whereby we identify the problem and did some analysis on the problem through doing some data cleaning. Yeah. So we got the data set, we pre-processed it. Then afterwards we shall build a model. Then we train it. Then we verify it. Then we test the model. Then we package the model. So after doing this, we can then go on and build the website to use to detect the babesia or babesiosis in the molecular images that will be uploaded. Next slide, please. Yeah, on this slide, yeah, here we were doing data set description and exploratory data analysis. So the data set we got it from this website here named the sources there. The classes we have in this data set, it is Babesia with 1,173 images, plus Modia with 843 images, RBC, which is the red blood cells, with 8,995. Then the one for leukocyl with 1,376. So the total images used are 12,000 images. So the type, these are microscopic smears that we got, which are 1,000 X modified, like through the Microsoft. The format, the JPEG and PNG. So the ED analysis we got severe imbalance between the Babesia minority class needs heavy argumentation, high visual similarity, Babesia rings versus Plasmodia rings. So here we're comparing between Babesia and Plasmodia rings since they are almost similar. So we have to find a distinction between them. So image size variations, the images have different sizes in between them. So let me hand over to my next groupment to present the next part.
Okay, all right. So briefly, as the former presenter has done it, let me take you through the EDA results. So as you see before me here, these are the complete dataset summary dashboards where we pasted the EDA results, the visualizations, and so on. So the first one is the class distribution. So here, this helps us, for example, to tackle questions, e.g. maybe how the imbalance we have in our class, and because if we don't do EDA, that means we are unable to determine whether we have classes of the same, of equal rows and columns, or of equal data set, of equal data, and so on. Therefore, here it helps us to detect imbalances between classes. Then we have the imbalance ratio. So here it will help us to detect which class is the rarest. For example, here you're seeing RBC as the rarest class due to the imbalance. Then the file size, yeah, the data sets. Every data set, for example, Babesia, it has its own its file size. For example, yeah, it can be having images maybe of 1 KB, 4 KB, and so on. So we have to detect all this in order to see we can match them properly and fight these anomalies. Then also, uh, uh, I can, for the interest of time, I may not peruse all through this and so on. Arthur, can you take us to the next slide? Okay, so class distribution, I already mentioned it early. Class imbalance ratio, same thing early also. Then also here, image dimensions. Yeah, images have different heights and width. Therefore, we have to determine for example, here, we have to determine the width and the height of particular images in a particular data set. For example, maybe it can be in Babesia, can be in RPC, that is red blood cells. So it helps us to make when we are resizing images, it helps us to fit them in a particular resolution. Yeah, then the file box size, it helps us answer questions. For example, the class specific quality ones. Therefore, here we can maybe use per class, pre-processing, and so on. Yeah, then next, you can take us to the next slide. Yeah, well, we have the metadata feature correlation heat map. So here it helps us. Remember that metadata is data that explains data. So it helps us to see metadata redundancy and so on. Therefore, it helps us to streamline our processing pipeline in order to see that our model achieves accuracy and so on. Then we have also RGB color space by class, where you see we spread it. They are using a scatter. We scatter them. We also have to identify patterns in different in different classes in all data sets for this case actually. Then also we had to make model architecture comparison. For example, we have the VGG, the RESTnet, the MobileNet, the EfficientNet, and that means a visualization of these architectures helps us to visualize on what architecture can best fit our model. For example, here I can make a conclusion that EfficientNet will be best for our model. Then also we have the impact of data augmentation techniques on accuracy. Of course, after detecting anomalies and so on, we have to make sure we do augmentation of data so as our model will achieve accuracy. Then we also have the expected confusion matrix. That matrix helps us to know where the model is actually struggling. So here it enables us to see to make error analysis baseline. Sorry, my Zoom is here warning me. But anyway, as I said, the confusion matrix helps us to see where our model is actually struggling, and therefore that we can fix it in a minor time. Okay, maybe for the interest of time, let me invite him to complete the demonstration of the developed product. Thank you.
We are out of time, so the demonstration is simple. We have a complete system workflow from sample preparation to diagnostic report. So from the beginning, we prepare the data, get a data set, we diagnose the data set through getting the doing the EDA and pre-processing. The user interface will have features like the upload, processing status, result dashboard. Yeah, this will be on the website after we make it. So sample diagnostic report with disease classification will be also provided. Confidence score, the treatment recommendations for according to what will be organized for each. Performance comparison, we want our model to be at least 92 or 90 compared to the 88% accuracy for people if they use a microscope. So the deployment scenarios, we want to at least if it can be deployed in teaching hospitals for different veterinary place doctors and so on. Regional labs, the remote clinics, processing time, we want it to be at least 3 to 5 minutes compared to the 30 plus minutes used for manual pre-processing. Conclusion, yeah. So in conclusion, we want to build a DL classifier for babesiosis detection using a public dataset. High potential to assist best veterinary doctors in resource limited setting. Model distinguishes Babesia from similar parasites effectively. So you want it to differentiate between Babesia and other diseases that or parasites that look like it. Limitations, we have limited level data sets, class imbalance, geographical variations. So as we saw from the data sets, we saw that we have a lot of data on one part or one part of the class, and the other classes have little limited data. So image quality, the image quality was low for some, low parasitic challenges, mixed infection complexity, no real-time mobile deployment yet. Yeah, we plan to make at least an Android app, limited Babesia data. At least we want to collect Ugandan data smears for fine-tuning. Next. So the next slide, we have future works. So in the future, we aim at expanding to a multi-disease detection, which will include an anaplasma, which is also another disease that affects cattle. We need a mobile app for vets and farmers to easily carry out this. Collaborate with vet labs in Uganda for retail, real-world validation. The recommendations integrate with national livestock health programs, open source dataset for East African researchers. Acknowledgement. I would like to acknowledge Mr. Gariwango for guidance and support, Makerere University courses, then mainly data for providing us with the data set. Thank you.